Hi, I'm making this video to cover the final project of my Introduction to Engineering Design course. For this final project, we explored the function of a photoresistor, or light-dependent resistor, by using it to receive and translate Morse code through voltage signals. Uh, for two messages, we plotted voltage across the photoresistor versus time to see how the photoresistor read each letter in the Morse code message. And we found that we were able to derive each Morse code message from its respective plot, which I'll show you in a little bit. Uh, but in case you didn't know, a photoresistor, or light-dependent resistor, is a resistor whose resistance changes depending on the intensity of the light to which is exposed. Um, As light intensity increases, the resistance of the photoresistor decreases. And this means that the voltage difference across the photoresistor will also decrease. So for this project, we used an Arduino Uno to uh, write and execute our program to read the Morse code. Um, What I have here in Tinkercad is just a simulation of the actual circuit we built. Obviously, in Tinkercad, I can't use the photoresistor and LED like I would in real life, because the photoresistor here can't sense the light that the LED is giving off. You can get kind of close by manually simulating the light intensity yourself, just with the photoresistor slider and the simulation. Um, but that's a little tricky. So this is just for display purposes. In the actual circuit, we had the bulb of the LED here sort of bent towards the face of the photoresistor so that the photoresistor could read the LED as best as possible. We have a 220 ohm resistor leading into the LED and a 15 kilo ohm resistor leading into the photoresistor. Um, I'm going to include the code in the description of this video. Um, but an advantage that the LED gives us is that we can use the LED to set certain brightness levels um, according to a dash, dot, and a space. Uh, for our purposes, we just set the LED bright level to 255, the LED medium to 120, and the off to 0. And these correspond to raw analog reading results. Um, we can also set fixed timing for each Morse symbol, the duration between symbols, the duration between letters, and the duration between words. Um, Now, to prevent our program from spitting out a bunch of measurements that we could not possibly keep up with, we decided to measure the voltage every half second. Now, what we did in our program was we started with a sort of calibration function that would set the LED's brightness to the bright, medium, and off levels and read the voltage for each level. Um, and we have this calibration in place just to deal with environmental conditions because you might be receiving Morse code in a bright or a very dark environment, and it's good to control for that sort of thing. If you also wanted to control for user input instead of an LED input, say you have a flashlight that somebody's shining and you want to read the Morse code off of that, you would have to include some more functions to deal with edge cases and variable times. I believe there is a program out there that has done that. I believe it has a GitHub. So I recommend looking that up if you are interested. Um, but in our program, we have a Morse tree set up just for basic capital letters and numbers. There isn't much functionality past that just because this was more of a test. But um, each time the program measures a voltage, we take the time in milliseconds, while um, while the current time, the difference between the current time and the start time is less than the chosen duration for a dash, dot, or space, uh, we read the voltage. Um, and then while we're transmitting code as well, we also have to check um, if our symbol is a dot, dash, or otherwise, and if our symbol is a dash, we set the LED to be bright. If it's a dot, we set the LED to medium, and if there's a gap, we set the LED off. Um, and we basically do this process uh, and measure the voltage every half second or so. I believe I already said that, but just summing it up. Anyway, after that introduction, let's take a look at the actual results. So I have the results here in an Excel sheet. Our first message we wanted to transmit and decode was hello. So we have a voltage versus time. Every voltage is in volts, time is every half second. Now from this chart and our calibration, we see that the bright LED intensity uh, for a dash is around 1.6. Medium LED intensity for a dot is around 2.1, and the off LED voltage is 4.5. So from here, we can sort of pick apart the original message looking at the dips in the voltage versus time plot. So for hello, the first letter H is just 4 dots. We can see 4 dips here around 2.1, and that is our letter H. Then there's a gap, a long gap, peaking at 4.5, and we know that this is a letter gap. And these smaller peaks are just, the gaps between each dot and the letter H. And we can see the next letter is here. That's the letter E, just 1 dot. If we keep going, the next letter is the letter L, dot, dash, dot, dot. We can see there's a letter gap here, and then dot, dash, dot, dot. So once you have the voltage and time taken from the Arduino data collection, it's pretty simple to plot this and then sort of decode backwards. And then we also did this for a name, Dr. Brody here. We can see in this name there's space, so this is just testing the reading of the space. We can see that worked correctly. There is a long gap here for the space between the R and B and Dr. Brody. That pretty much covers it. So thank you for watching.